Okay, this is example 14.7 from the book. And before we get to the example, we've had a lot of triangle delta things going on. So let's review real quick. So delta H is the change in enthalpy of the reaction. That's like an energy change. Does it gain energy? Does it lose energy? That number tells us if it's an exothermic reaction or endothermic. Is it producing energy or releasing energy, or is it consuming, might not be the right word, or is it like taking in energy or absorbing? There's the word, absorbing energy. Next, we have the change in S, delta S. That's our change in entropy. Entropy is how much energy we have available of the, I can't remember the word, it's not molecules, whatever. How much of the stuff do we have that's organized or in order enough to actually do work? The bigger the change in S, the more disorder we have, or the more entropy is kind of like chaos. So when we find the change in S, we're trying to figure out, does it gain or lose entropy? Does this reaction make the molecules more ordered, or does it make them less ordered? And then the delta G, or the change in G, that's our Gibbs free energy law that we just learned about, or Gibbs free energy, not law. That is combining the change in H and the change in S to help us understand whether or not this obeys the second law of thermodynamics. And what it's finding out is it spontaneous? If it is negative, then the reaction is spontaneous. And if it is not negative, or it's positive, the reaction is not spontaneous. And this one takes into account whether it's endothermic or exothermic, and then subtracts the change in entropy multiplied by the temperature, because the temperature will often help decide or determine whether it's going to be spontaneous or not. Okay, so now that we've had a quick review of that, let's look at our question. The pink boxes are things that you should have memorized that are on the slides that I've made as reminders of the memorization of the, like, you have to know these things. All right, so determine whether or not the following reaction is spontaneous at 25 degrees Celsius. So to do this, we are going to start by finding our change in H, then we're going to find our change in S, then we're going to put them together with our change in G, and that will tell us whether it's spontaneous or not. Because it's at 25 degrees Celsius, we are able to use the absolute charts, and they're in the back cover of your book, so you don't have to go flipping through the whole chapter. The standard enthalpies of formation is your delta H, has a little F and then a degree symbol. That means 25 degrees Celsius is the temperature that that chart is appropriate for, and then the absolute entropies is right underneath that, and that's your has the S. Okay, so let's start with the first one. So change in H. And remember, we're going to start with our product. So we're going to start with carbon dioxide. There is one molecule of that, 1 mole of that, and that is negative 110.5 kilojoules per mole. And then next we have H2O2. I'm probably not going to be able to write small enough for this. Let's see if I zoom in. That way we can just see the problem. Okay, next we have H2O2. We have 1 mole of that. And then the number from the chart for the H2O is negative 241.8 kilojoules per mole. Let me look at the chart real quick so I can see where those are. So the CO is on the second column, 3 down, and then H2O in your book, the gas form is the one we're using. That is also second column, second to last one. All right, and then we are subtracting the reactants. So again, we have 1 mole of each. And for carbon dioxide, sorry, I'm flipping back and forth in the book. That one is negative 393.5. That one is also in the second column. 393.5 kilojoules per mole. I am running out of room. I should have made myself more room. And then the last one we have is our hydrogen gas. 1 mole. And for hydrogen gas, we have, that one, I don't even need one for that one. hydrogen gas is just in its natural element. At this one, it's its natural state, so it's just going to be 0. So I'm just going to put 0 and just not worry about the units since I've run out of room. Okay, so let's calculate these. The moles all cancel. Everything is just 1 mole of this and 1 mole of that. So really, we're just adding and subtracting. So you know how to put that in your calculator. We're going to end up with 41.2 kilojoules. That's our change in H. So we're going to hold on to that for just a minute. We're going to come back to it. First, we're going to do our change in S, and then we'll use that one. Okay, so now we're talking about change in S. We're talking about entropy. So we're going to use our entropy table to find these. All right, so in this one, we're going to again start with 1 mole. And for CO2 and, CO, not CO2, in gas form, that is in your second column of the absolute entropies table, third one down. That's 197.5. And that one's in joules per molic. And then we have 1 mole of H2O in gas form. And for that one, H2O gas form, that's also in the second column. It's kind of the fourth one from the bottom. It's 188.7. 188.7. And that one's in joules per molic. I know that molic is not a term, but that helps me to remember what's supposed to be on the bottom when I'm writing it. All right, and then carbon dioxide, we have 1 mole of that one. I'm going to run out of room again. Carbon dioxide, it's in the second column, second one down, that's 213.7. 213.7, that's joules per mole times Kelvin, or molic as I call it. And then for this one, for the entropy, we do have one for even like our gases in their natural state. I'm just going to put this down in the next line. Minus 1 mole. And then for the hydrogen gas, that's going to be one of the ones at the bottom in the yellow part of your chart. That's 130.6. 130.6 joules per molic. All right, so now we're going to mark out all of our moles so that we end up with just the other units. And again, everything's just 1, so it's just a lot of adding and subtracting, and everything's to the tenths, so it's really easy. Whatever you put in your calculator, whatever you get out, it's going to be it. So we have 41.9 joules per Kelvin. All right, now we have the 2 pieces that we need for our problem. Let's change color so we can keep track of where we are. All right, so for our change in G, we're going to use this equation right here that we've just recently learned. So our change in G is the change in H minus the T times change in S. All right, so in this one, notice that we've got to deal with some units here because we're going to be multiplying the temperature times this number, which is in joules per Kelvin, or J/K. We need to have our temperature be a K so that when those units cancel out, we're left with just joules. And because we're going to be adding it to this also needs to be in joules, but it's not, it's in kilojoules. So we need to change both of those. So let's go ahead and do that. So for this one, let's put an arrow going this way. So we're going to change this number to joules. So our change in H, if this were on real paper, I promise this would be so much more organized and easy to read and not nearly so messy. Okay, so we're going to change this to joules. We know that there are 1,000 joules for every 1 kilojoule, which means this number is going to get a lot bigger. It's going to move, it's like times 1,000. So 1, 2, 3 decimal places over. All right, so there's our new number. It still has the same number of significant digits. It's just in the correct units now. And then the other one, remember our formula to change temperature is we have to add, but because the Celsius temperature they gave us is 25 degrees, when we add, oh, drop a pen. When we add 273.15, that we're gonna end up rounding it and dropping it, and so it's gonna become 298 Kelvin. And if you're like, what? 25. I'm not actually sure why I wrote that there, because that's not the appropriate place to write that. This one doesn't need to be changed. This up here is what I'm changing. This one is my 298 Kelvin. 25 plus 273.15. When you add those, you get 298.15, but because this only goes to the ones place, this number can only go to the ones place. So that's why we just rounded this to 298K. All right, just in case you were like, what just happened? That's what just happened. All right. This light blue color is just too hard to read. All right, so we're going to take our numbers that we have. So change in H is 41,200 joules. We're going to subtract the temperature in Kelvin, which is 298K, and multiply that by the change in S, which is 41.9 J per K. All right. Let's scratch out the units using this blue so it doesn't get too messy to read. All right, so we're going to put that into the calculator. And we'll talk about significant figures if it becomes a need. So 41200 minus, we're going to multiply these two numbers, 298 times 41.9. All right, and the answer we get is 28,713.8. So let's look real quick. We started by multiplying. I probably should have done that in pieces. The multiplying part, to make sure that we kept the right number of significant digits. So let me go back and do that real quick. So 298 times 41.9. So when we do those two together, we can only keep three significant figures, which is 12,500. And so we need to do that part first, because since we've got this little equation involves both multiplication and subtraction, we have two different significant figures rules that we're having to follow here. So the first one is the multiplication rule, which is how this number gets rounded to only three significant digits, which would just be these three. So let's go ahead and write that down with our units that are remaining. And the good thing is that both of these numbers had their last decimal place in the hundreds place, and so it should, unless it, like, you know, if they were both the same number and they subtracted to make a zero there, that would be problematic, and we'd have to use scientific notation to show that that zero mattered. But because 2 and 5 aren't going to subtract to make zero, the number we get is already correct. So 28,700 joules. So that is our change in G. All right, so they didn't ask us what the change in G was. What they asked us was whether the reaction was spontaneous or not at this temperature. And so we use this information right here to answer that question. Because our G is positive, our change in G is positive, this is not spontaneous as a reaction.